we want to find the surface area of this paraboloid that's above the xy plane. So that would be this paraboloid here, but all of it, not just the quarter of it. Okay, so the first thing, we need to find a parameterization. Now I'm going to do this two ways. I'm going to do it with a rectangular parameterization, so that just this one. And then I'm going to do it with a polar coordinate parameterization. So this is R. And the parameter domain, well, we want to have 1 minus x squared minus y squared be greater than or equal to 0. So this means x squared plus y squared is less than or equal to 1. In other words, we want to have s squared plus t squared is less than or equal to 1. So that's the parameter domain. The parameter domain is the disk of radius 1 centered at the origin in the ST plane. Okay, now we need to compute RS cross RT. So I'll do RS cross RT. So RS is 1, 0, minus 2s, and RT is 0, 1, minus 2t. And the first component of this is going to be 2s. The second component is 2t, and the third component is 1. So this means that RS cross RT, the magnitude of that is equal to the square root of 1 plus 4s squared plus 4t squared. And so it means that the surface area is going to be the integral over the disk of radius 1 centered at the origin in the ST plane of 1 plus 4s squared plus 4t squared, and then ds dt, where here this is the disk, d is the disk of radius 1 centered at the origin in the ST plane. Okay, now pretend that this integral came up to you. Like I just said, do this integral. Completely forget about all of the where this came from. Okay, if I just said do this integral, how would you do it? Well, you're integrating the square root of 1 plus 4s squared plus 4t squared over a circle. So you should probably think, let me do polar coordinates. So theta is going to go from 0 to 2 pi. T, or r, sorry, is going to go from 0 to 1. Don't forget to write the r, dr, d theta, and now the function that you're going to integrate is 1 plus 4r squared, because in polar coordinates, s squared plus t squared is equal to r squared. So explicitly, s, say, is equal to r cosine theta, and t is equal to r sine theta, for example. You could do it the other way around, it doesn't matter. Okay, so this is how we do the problem in Cartesian coordinates. Now I'm going to do the problem where we start in polar coordinates. So now and I'm going to do that in orange. So now the parameterization is r of theta s. Actually, I'm going to do r of theta t. So for polar coordinates, remember, typically we use theta and r. But since I'm using r for the name of the parameterization, I don't want to use it as a coordinate. Okay, so r of theta t is equal to t cosine theta, t sine theta, and then z is 1 minus x squared minus y squared. In polar coordinates, that's 1 minus t squared. The parameter domain are going to be all of the thetas and t, where 0 is less than or equal to theta is less than or equal to 2 pi, and t is less than or equal to 1. And of course, t is always bigger than or equal to 0. Okay, this is the parameter domain. So now we need to compute r theta cross rt. So this is I, this is j, this is k. R theta, take the derivative of r with respect to theta. This is minus t sine theta, t cosine theta, 0. Now we take the derivative with respect to t, so this is cosine theta sine theta minus 2t. And the first component is going to be minus 2t squared cosine theta. The second component is going to be minus 2t squared sine theta. And the last component, there's going to be a trig thing that helps us. It's minus t sine squared minus t cosine squared. So that's just minus t. And then the magnitude of r theta cross rt is equal to the square root of 4 t to the power of 4 cosine squared plus 4 t to the power of 4 sine squared theta. I forgot the theta with cosine, plus t squared. Okay, now there's going to be another trig identity that helps us. This is equal to the square root of 4t to the power of 4 plus t squared. And what is this equal to? This is t times the square root of 1 plus 4t squared. Okay, so that's r theta cross rt. We're integrating this over the parameter domain. So t goes from 0 to 1. Theta goes from 0 to 2 pi. And we're integrating 1 plus 4t squared t dt d theta. Okay, so notice that we're integrating in polar coordinates. I mean, what we're doing is we're integrating in polar coordinates, but we don't have to add an extra, we don't have to multiply by an extra t here aside from what was already there. And the reason is because something that I've hinted at before, but won't be able to go into much detail, is that essentially when we're this magnitude of rs cross rt, this is a certain type of Jacobian. And so the difference in the way that we did the problems in Cartesian coordinates and polar coordinates, in Cartesian coordinates, we basically went from the ST plane to the surface integral to polar coordinates, or really the other way around, from the surface integral to the ST plane to polar coordinates. So we have the magnitude of rs cross rt, and then we multiply that by r. So we have two transformations, so we have basically two Jacobians we have to multiply. Now, in the way that we just did it here, notice what we did. We went straight from the surface. To polar coordinates. So we just have one Jacobian to multiply by, and it turns out that Jacobian is exactly the product of the two Jacobians from the other way that we did it. Because notice what's happening here. The integral in red that we just saw is the same exact thing as the integral in orange that we just did, which makes sense because we're just computing the same thing in two different ways. Okay, so both methods are correct in the sense that you'll get the right answer. It really is just sort of a personal preference which one you want to do. I think for a problem like this, polar coordinates are best because you are integrating over a circular region. But maybe if we had been doing the same thing, or maybe if we'd had the same surface, but we wanted the part that was over a rectangle, then rectangular coordinates would have been better. Anyways, if some of this doesn't make sense, watch the video again and try to wrap your mind around some of this stuff. I know that it gets confusing and it gets tricky, but the good news is it gets more confusing and more tricky as we go.